We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
The issue of feral children, as you know, have been with us for a very long time, and largely through luck. I happen to know two of the living ones. The luck is caused entirely by television, newspapers, and I'm sorry to say, not by very much scientific evidence. My field has been primatology. I study baboons, monkeys, people like that. And one day I received a call from BBC saying that they had in hand a boy who'd been raised by monkeys, and would I care to go to Uganda and investigate the matter? Who can turn that down? I had actually got my interest from the Wolf Girls of India. When I was a student, we read about and discovered that this was maybe true and maybe not true. I have now visited John Sebayuna in Bombo, Uganda 5 different times, filmed 5 different documentaries. I've known him since the age of 4 to approximately 17. As you know, when you do documentary television, the control lies with the director or sometimes the producer. I think I'm very fortunate to have known John over these many years, but I have no scientific data for you. I said I had a little bit of neurology, but I really have precious little because nothing's been done in that direction. The first time I met John, I very carefully kept out of his way for a couple of weeks, but watched him while the TV people went about their business. John lived in, as I say, a village called Bombo. The local story, and I confirmed this by chatting with people who lived there who spoke enough English for us to have a conversation. His parents were alcoholics. They got in a fight. They got in many fights. Some fire started. His shack burned down. And the story is that he was left in this jungle. Well, the word jungle is an English word, and it doesn't convey accurately the terrain. The terrain is more like chaparral that you would be familiar with here. Who claimed he was raised by monkeys? Well, he actually was captured by a woman named Millie and allowed to live in her shed. She thought that he had been raised by monkeys, and that story became very common and reached the British newspapers and then got the attention of television. I've never heard John directly say that. But although John's been in an English-speaking school now for 15 years, He does not really speak the language, and I'm not sure he understands very much. So my job was to find out, was he raised by monkeys? So I took with me the Handbook of Eastern African Primates. And I showed it to him and asked him, through a translator, to tell me who the monkeys were. And so he picked out gorillas. Unhappily, there are no gorillas in that part of Uganda. So I tried again the next day, and he picked out vervet monkeys. Well, there's a lot of vervet monkeys in that part of the world. And they're very interesting. They travel in rather loose troops. They tolerate strangers. They don't seem to mind people joining the group or leaving the group. And they have a peculiar habit as they forage of examining the food, the seeds and things they're picking up, and then throwing half of it over their shoulder. And it occurred to me that in the mind of a 6-year-old boy, this would look like being fed. John is now 17 years old. He now has a permanent companion who's his translator. The permanent companion was educated in Sussex. He speaks beautiful English, and he speaks for John. The only physiological evidence I know of occurred during shoot number 5, when I was asked to take John to the local medical center to have an MRI done, to have a brain scan done. I thought about this overnight and decided I didn't want to do it. I didn't like the TV image of a white American taking a black African to the hospital and telling him to lie down and take this test. So I told the director that the next morning, expecting to be fired. But since I wasn't being paid, it didn't make much of a difference. And she said, "Oh, that's okay, I'll have his mother do it." And that's the way it was actually done and the way it appeared on screen. The readings were eventually done here in America by a neurologist who said that it looked as if he'd fallen out of a tree. So neurology has become much more of an exact science than I had ever learned. That leads me all too briefly to Cow, born in Los Riscos, southern Chile, who is almost exactly my age. If he's living, I have heard rumors he's not, but I have no reason to believe one way or the other, except that not many people my age are living, so it's quite possible. He was known to be raiding garbage in the village of Los Riscos. He was taken to Santiago to what was either a hospital or an orphanage. He got an excellent medical evaluation for its time, including an EEG, which was unusual at that time. I have that record. The record suggests that he either suffers from epilepsy, schizophrenia, or oligophrenia. That latter is a term I don't think has been used in many years. What's important about Cow is that he was adopted by his speech teacher, Berta Riquelme, and she lived with him in her home for about 12 years and kept daily records of what she was trying to accomplish. The only thing like that in the literature is 150 years old, The Wild Boy of Aveyron, where Dr. Itard kept a daily record, which, by the way, is beautiful literature. And although he's asking for money, that's the purpose of the article that Dr. Itard wrote to the French Academy. It is just a wonderful story of human love and compassion and frustration. And that's what happened with Cao, as was true with Dr. Retard's charge. The onset of sexual interest spelled doom. The behavior became uncontrollable and embarrassing. Cao actually went to school. He learned to count to 10 before he became too difficult for Berta to handle him. He was apparently taken over by a foster brother who later wrote a book about him, a fictionalized account, and he said it was a fictionalized account. Where I'm going with this is when the TV people got a look at this, they decided that they needed a puma. And so on Chilean television appears 2 clips. They are led by a puma running through the forest holding a baby in its arms. This is the first time in the history I've told you that there is any evidence of Cao being raised by an animal. But Cao adopted the story and was pleased to tell people about his life being addressed by a puma. At this point, BBC comes in again and wants to film this. Their director goes to Los Riscos, where Cao is now living on a farm with his foster brother. This is recent. I am on my way there with trepidation. I do not understand Cao's Spanish because it is actually an Indianized Spanish, which I've shown it to much more literate Spanish speakers who say, no, I cannot understand this. It's and Indian, it's native. When BBC actually examined the situation, the foster brother said, I do not like this. We have here a 80-year-old person who has fought a tough fight, and he is now happy and content. And we see no need at all to have any television coverage done. And to their credit, BBC said, we don't film people who don't want to be filmed. So there is no further record of Cao. Both of these boys, in my opinion, suffer from some form of mental deficiency. In the one case, John of Uganda, his family has pushed him forward. He's appeared on television in many European countries. He's sung in choirs. He's been to America. He's traveled a great deal. I've been to the school where he is a student. In my opinion, he is a mascot and a pet in a school which is called an orphanage, but actually is one of those British schools where everybody wears uniforms and learns Latin, neither of which interests John of Sebeyuna very much. Cao appears on Chilean television in these 2 shorts. In the one of them, he has a new pair of shoes, and he patrols Los Riscos and wants people to admire his new shoes. We know really very little more about any anatomical or physiological evidence about him. The key to all of this is, why do we want to understand feral children? I'm going to conclude with this comment. Dr. Retard was interested in knowing whether he could take a child and teach him French culture. It was actually, of course, the time of the French fascination with the theories of Immanuel Kant. And Dr. Itard was interested in what we are given with our brains and what we must learn with the a priori and the a posteriori. The parents of, the foster parents of John Sebayuna seemed to have no specific need other than the discovery that they adopted. They adopted, by the way, some 32 children, all of whom went to the school orphanage. But John provided a rather steady income for the school over 15, 17 years. I know them, I've met them many times. They are people dedicated to their work, but they show no particular interest in how the boy might learn or what he might learn. In the case of Cow, Berta, his foster mother, was alarmed that he had not been baptized. And the very first thing done in the hospital was that. And her interest is in seeing whether he would acquire what she considered appropriate religious values. The question then becomes, what can we learn about feral children? I think we can learn a great deal about the human brain. Not theirs, but ours. What is it that prompts us? You've heard a moment ago about the Wolf Girls of India. Reverend Singh's interest in these girls was in seeing whether they might not have a native a priori understanding of God. The moral lesson each of us brings to research and to our interests, our culture, our particular way of understanding things. When I mentioned feral children, almost the very first question is, were they really raised by animals? I'm sorry to disappoint you. I have no idea. I doubt it. There are 4,000 cases about which there's some written record of human children being raised by animals. Not a week goes by that I don't get a letter from someone saying, "You study feral children? Come, I want you to see the kids next door." My wife and I, having raised 3, we understand exactly what we're talking about. To get serious again, I think what's important about all of these situations is why humans want to know. Because they have a priori ideas of God, because they need religion, because they provide income. So I urge you, and you're going to hear some fascinating papers today, as am I, to always keep in mind what I would call the meta-psychology of these issues as to why we want to know what we want to know. Because I suspect that is the true value of all the time and money that's been spent on, are they really feral? Were they really raised by animals? It says much more about the categories of our minds as humans and as investigators than it does about the children themselves. Thank you very much.
So I am going to be talking about what happens when children get exposed to stimulation, not when they get deprived. And I'm going to focus particularly on language acquisition. I need to start by just saying a couple of words about what is a language and what would it mean to learn it. So in a very simplified fashion, what I want to say is that languages are combinatorial systems that involve figuring out what the units are at the lowest level sound segments, but then those combine If you happen to be exposed to a sign language, it's hand shape or movement segments, but analogous to sound segments. Those get combined to form what are called morphemes, which is the smallest combinations of sound that have meaning. And morphemes get combined to form words, and words get combined to form phrases, and phrases get combined to form sentences. So the point here is that languages around the world are big combinatorial systems. And what you have to do when you're learning a language is to figure out what the combinatorial system of your particular language is. So I want to focus on two questions. One of them is, what makes humans so incredibly good at learning languages? And the second is, why is this particularly true of very young children when adults are really typically better at everything than a young child, but young children are remarkably better at learning languages? So how do we understand that? So I want to start by talking about something that we have called statistical learning. This is work that I've done for a long period of time with Richard Aslin. And what we mean by statistical learning is that we and many other people have found that humans, especially children and including infants, are very, very good, remarkably adept at very rapid pattern learning. And we call it statistical learning because what we have suggested is that part of what they're doing when they listen to streams of sound, for example, I'm going to give you an example of this in a moment, is keeping track, absorbing naturally, that is, the brain is naturally absorbing from exposure the statistics of language input, by which I mean the brain naturally sucks up and keeps track of the frequencies of individual sounds and their occurrence in the streams that you expose us to, and the frequencies of co-occurrences of sounds that occur next to each other or even some distance away. And we use these statistics to acquire language. So what we have suggested is that part of the reason that we're so good at learning languages is because we have evolved a remarkable ability to acquire this kind of statistical information and use those statistics to construct the rules or the patterns of the languages that we're exposed to. We also, I'm going to show you in the second part of my talk, there are some internal inherent constraints and biases in the nature of this learning that change with maturation, and that's what I'm going to argue makes children better than adults at doing this kind of learning. We're really good at this when we're babies. We decline in our ability to do this over life. We all know you can still learn languages as adults, but you're not so great at it. So I want to illustrate with a problem that we started studying with Jenny Safran quite some time ago, which is the problem of word segmentation. And this is just an example. We've gone on to look at much more complicated problems, but I think it will help to give you a clear example of what I mean by statistical learning. So when you start being exposed to a language, the stream of speech that you get exposed to in any language of the world is actually continuous. There isn't any little white space in between the words the way there is when you look at print. So how do you figure out what the words are? That seems to be an early step that you have to figure out in order to learn the language. Which sequences of sounds form words? And what you see here is a waveform. Just showing you the high places here are, these places are lots of sound, high amplitude, and these places are less amplitude, less noise. And the red lines I've drawn are actually the places where you would hope that there would be some little white space. Those are the breaks between the words, but there are no breaks. So the point that I'm making here is the voice does get loud and soft as you listen to a sentence, for example, but it doesn't have anything to do with where the breaks between the words are. You're going to have to figure out what the words are and where the breaks between them are by some other method. So we did, quite some time ago, an experiment with Jenny Safran, looking at how you could figure this out. And this was originally based, as I'm going to show you in the next slide, on eons of linguistics. Linguists do this all the time, and if you look at a famous textbook, any famous textbook of linguistics, you'll find that what it tells linguists is when you listen to a new language, there's a bunch of statistical cues. They're usually called distributional information, not statistics, about how to tell what the units are. And the idea is that the words over a big body of speech are going to be the consistent sequences of sounds that you hear repeatedly. And the sequences that are across a word boundary are going to be much more changeable because words don't always occur in a fixed order. So what we suggested was maybe even babies, not just linguists, but maybe even babies, could use this pattern of distribution of sounds to figure out what the words are. And the idea in statistical terms is perhaps learners can use transitional probabilities, the likelihood that if you hear one particular syllable, it will be followed by another to figure out what the words are. Now, I want to emphasize, this would be easy if you had a tape recorder and a computer, sort of. It's really, really not so easy if all you come with is you're a baby and you come with a brain. Somehow, large bodies of information would have to be stored in a relatively raw form, and then your brain would have to be busy doing these computations. And I'm not going to be able to give you the method by which the brain actually does this, but I want to show you that it does. So this is following Zelig-Harris, 1955. Zelig-Harris is my academic grandfather. And this was sort of his instruction to linguists, not to babies. The idea was if you hear a sequence like pretty baby or pretty flower over a body of speech, pretty would be sound sequences that you might hear recurrently, but T-bay would not. T-bay would occur every once in a while when you happen to hear pretty followed by baby, but not on a consistent, high probability basis. So the question was, would you be able to figure this out without any meaning? So this is an experiment done with no meaning, no intonation, that is, no variation in the way that the speech is produced. It's all run together. It's run together in this particular experiment we did with adults, run together for 20 minutes. So this is an excruciatingly boring experiment to be in. And people listen to this, and then we ask them if they can identify the words. We don't expect that they'll do this consciously. We ask them if they can choose between the sequences that were the secret words and the ones that were across a word boundary.
Do ta ba tu ti boo do ta ba ba boo poo pa tu be do ta ba pi da boo ba boo poo pi da boo boo.
So that fascinating stream is what you hear. And secretly, because, let me go back to the list of words, because the syllables in this experiment are used in several words, there will be transitions like between do and ta that are very high frequency, and there will be sequences like ba to pa that will be low frequency, but it goes up and down because the syllables are used in different words, different numbers of words in different positions. So this is actually a piece of the stream shown at the bottom, and what you're seeing plotted here is the transitional probabilities. What's the probability that if you hear do, it's going to be followed by ta? And the important thing to notice is that the word boundaries are places of dips in the transitional probability, and the insides of words are relatively higher probabilities because that's what it means to be a word. Part of what it means to be a word is that you hear these sequences recurrently. So our question was, if we exposed people to this incredibly boring stream of speech and paid them to listen, we paid them $7.50, lots of money. And then at the end, we gave them do ta ba versus boo pi da. Which one would they think sounded more familiar? That was the question we asked them. So here are the results for adults on the left and children, 5-year-old children on the right. This particular experiment we did while everybody was coloring. because we couldn't figure out how to get 5-year-olds to hold still. They weren't enticed by the 750. So everyone was coloring, and they heard these streams of speech, and then afterwards we asked them to judge, and this is the probability that they pick the word as compared with what's called the part word, the end of one word and the beginning of another. You can see that people absorb this information incredibly well. They do very quickly figure out which ones are the words. We also did this experiment with babies. So this is a drawing of a parent holding a baby. The parents don't get to listen to the speech, so they won't jigger the baby when the right answer comes up. But the babies are just sitting listening. We simplified the word structure. The babies listened for 2 minutes. And then we gave them the 2 alternative forced choice version in Babyland, which is light a little light over on the right, and babies will naturally look. You don't have to train them to do that. And then we would play a word or a part word, and they will get very bored when it's a word because those are the things they've learned. And they will show less looking time to the words than if it's a part word, which the fact that they discriminate suggests that they can do this as well. We also subsequently did it for things that are not language. So it turns out we're not just good at absorbing auditory patterns in language. We can do it for tone sequences. We can do it for visual patterns. We can do it for lots of things, including noise sequences. Those are the same kinds of statistical regularities built out of noises from the Mac. So people can learn this. It took a lot longer. This is not a very evolutionary, natural set of stimuli, but they can do it for those kinds of noise sequences as well. So in this line of work, our findings are that there's a mechanism for computing sequential patterns online extremely rapidly that we find in adults as well as 8-month-old babies. It's a remarkably complex ability, so I didn't tell you, like, how many syllables do you have to learn? How many probabilities do you have to be able to keep track of and compute in order to do this task? But it's a lot. And there were only 4 words in the baby experiment and 6 in the adult experiment. In our natural languages, we learn about 40,000 words. So to do this kind of task requires a lot of computation, but it does seem to be something that the human brain is extremely good at. And of course would be useful for learning complex patterns in a number of domains, but especially language. So what I've said so far is that humans, and including both babies and adults, are really good at doing these kinds of implicit learning outside of consciousness, but absorbing some of the patterned regularities that we get exposed to that enable us to learn language, we think. But what we've also found in subsequent experiments that I've been doing with many of my students is that we're very good at this when we're babies. We become not so great, although somewhat okay, at doing these kinds of tasks as we get older. And we've been looking especially at what is it that changes, what's so good about babies, what is it exactly that they're good at, and I want to just give you one example of the kinds of things we found. So just to demonstrate that when we start young, we're actually better at learning languages. These are old data from Jackie Johnson and myself looking at second language learners of adults, and this is looking at groups of people whose families moved to the United States when they were at different ages. And what's being plotted here is their age of arrival in the United States. That's when their family moved. We didn't make them. They did it by themselves. But then we tested them when they had been here for 10 years. We gave them very simple task, judging sentences of English. And you can see that you get these enormous age effects. I want to also draw your attention to the fact that this was a 276-item task, and the bottom of my plot here is 200. So everybody's pretty good at it. I'm kind of exaggerating the age effects by the way I've plotted the data. But you get both age effects, and people in their adult life are still okay. But why are children better language learners than adults? And there are a couple of different ideas about this. One idea is that there might be a special linguistic ability, that is something special to language that diminishes with age, some kind of language faculty that gets worse as we get older. What we have suggested is that this complex pattern learning ability that I talked about really works especially well when we start with limited abilities, when we're very resource limited, when we don't have the ability to retain very, very complicated, detailed information about the speech stream, and when the statistics that we can compute are fairly simple. And so this is part of a set of hypotheses. I've called it less is more. Jeff Ellman, who was at UCSD and beloved by those of you who knew him, including me, called a similar hypothesis starting small. And the idea is perhaps it's because of starting small at these abilities that we actually can focus on the most prominent statistical patterns and then acquire gradually those that are less prominent, less regular. And I want to show you some experiments that we've done to look at this hypothesis. These are data that are actually natural language data looking at a child, Simon, who was a deaf child whose parents were late learners of the language that he was learning. He was learning American Sign Language, but we brought this into the lab and we can show the same phenomena in spoken languages. And the idea here is that Simon learned the language from his mom and dad, who made lots of mistakes, and they were very inconsistent. He didn't actually know anybody who used this language other than his mom and dad. And yet you can see that on a task when he was 9, he was better than his parents. And so we got interested in trying to understand this phenomenon and brought it into a laboratory experiment. And what we think is going on that I want to show you in experimental data is that when you give young children inconsistent input, they find the thing that's the more consistent out of a kind of noisy exposure, and they form a very strong rule about the more consistent things that happen. And they don't learn the mistakes. They don't learn the occasional regularities. They really regularize or exaggerate those things that are somewhat consistent in the input that they receive. Adults don't do this. Adults learn it all. They probability match, and that's not very useful at learning a language. So we've done a bunch of experiments with children and adults, giving them inconsistent input in the lab. And these are miniature languages. The children are 5 and 6. And we give them a variety of exposure sessions, but they get little words after nouns, ka and po, that are on purpose inconsistent. So I want to just quickly show you the paradigm. We show them little movies that they hear, and they hear sentences that are in an artificial language. And they see things like the bee headbutting the giraffe. These are just stills. And then after that, they see novel films. They get the beginning of the sentence, which in this case is a verb, and they have to speak the language after 5 days of exposure. And everything's very regular, but ka and po occur very inconsistently. In the first experiment that I want to show you, they get ka 67% of the time after a noun at random, and 33% they hear po. And if you do this with adults, you can see that they perfectly reproduce the inconsistency. These are actually the data. Adults produce 67% ka and 33% po. Here's what 5-year-old children do. These are the adult data moved over, and this is the children. Children do 90% ka and 10% po. So they find the thing that's the more regular and do it more often. We did this also with a 40% condition where they're only hearing ka 40% of the time, po 20, and the rest all scatter. You can see that adults, again, do 40% when they're presented with 40%. Here's what kids do. The thing they hear 40% of the time, they still do almost all the time. So what the kids are doing is regularizing even inconsistency. They're doing statistical learning in a funny way. They're changing the statistics into things that are very regular that in linguistics we call rules. And adults are reproducing the noisy, crummy statistics that they get exposed to, which is a skill in and of itself, but not very good for learning languages. So let me turn to my conclusions. We think that in many experiments, I've just given you one example, that statistical learning is a very important part of language acquisition. Humans are remarkably sensitive to a variety of statistics that reflect linguistic distribution of elements in the speech stream. And they use these statistics to acquire the rules and structures of natural languages. But what I want to emphasize is statistical learning is not veridical, at least not in children. It's not just learning whatever's in the input. That is not what we do when we learn a language. Statistical learning is also not the same over age and maturation. Children learn somewhat differently than adults. They make inconsistent usages more regular. We found this in about 10 experiments now. And they also favor certain types of patterns over others, so we've also done experiments where we give them things that are like what happens in languages of the world and things that are not like what happens over languages of the world, and they change the languages that they get exposed to into something more like real languages. So there are clearly biases about certain kinds of patterns that show up in the laboratory that also seem to shape languages of the world. So we think these biases and constraints on learning may help to shape languages over generations. Thank you.
So language co-evolved with the human brain throughout evolution of Homo sapiens. While language develops automatically for most children without the need for explicit instruction, as we've been hearing today, there are many genetic as well as environmental factors that are known to affect language development. These include hearing loss, cognitive impairment, motor impairment, emotional deprivation, as well as brain damage and syndromes such as autism. However, there are children who appear to be developing completely normally without any of these problems who nonetheless fail to learn language at or near the expected age. These children are diagnosed with specific language impairment, known as SLI, of unknown origin. As they grow up, most of these children go on to have other verbal learning deficits, such as dyslexia. I've focused my research over the past 45 years on unraveling the mystery of SLI. I believe that understanding developmental language disorders, specifically SLI, may help us better understand the evolution of language itself. So let's start at the beginning. While it's true that language is innate and does not need to be explicitly taught, quality language exposure is critical for language development. Well before the child begins to talk, oral or spoken language development begins with an infant being exposed to the sensory and perceptual features of the complex acoustic waveform of the speech they hear all around them. Hi, baby. What a pretty baby you are. But of course, the infant doesn't know any words. So what is their language? What is their brain actually receiving? As we speak, we move our speech articulators from one position to another very rapidly in sequence to form sequences of sounds called phonemes, words, and sentences. The complex acoustic signal that's produced as we speak, as we see here, comprised of a combination of acoustic features like frequency, from low to high, amplitude, which changes very quickly over time as we speak. As we just heard from Dr. Newport, infants who hear normally and have sufficient exposure to speech begin to detect frequently repeating patterns and learn the statistical probability of which acoustic patterns are likely to occur together or sequentially. Their brains begin to chunk the ongoing speech waveform into smaller repeating segments that acoustically represent phonemes and syllables in their language, such as ba or da. Phonemes such as ba and da, shown here as frequency, over time are the smallest acoustic segments of sounds that can change the meaning of a word in a language. For example, when the phoneme B is changed to D, we hear bad instead of dad. Phonemes are the building blocks for syllables and words, so detecting, segmenting, discriminating, and neurally representing the phonemes of our native language is an essential prerequisite for all higher levels of oral language development. For humans, when we hear speech, beyond detecting or hearing the sound, which occurs at the level of the ear, in order to be processed as speech, the complex acoustic signal has to be transmitted up through the nervous system to reach the auditory cortex. When an infant has a peripheral hearing loss, is deaf, this acoustic processing is disrupted, leading to great difficulty developing oral language. The deaf can learn sign language by bypassing the auditory system. Now let's turn to the mystery of SLI, specific language impairments. We know these children have normal hearing, yet they're impaired in speech processing and language development. What was not known when I started my research was whether these children might be impaired on any higher level nonverbal auditory processing that are critical for speech perception. To investigate this question, I developed a hierarchical series of simple nonverbal auditory processing tasks to systematically test each level of sound processing along the auditory pathway from the ear to the brain. This auditory processing test, now known as the Tallal repetition test, used only two complex tones, one higher in frequency than the other, and two buttons. First, only one tone is presented at a time, and children are trained to press the top button on a response panel for the high tone and the bottom button for the lower tone. Very simple task. Once this association is learned, two tones are presented in sequence. The two tones are separated by a gap of silence of various durations, known as an interstimulus interval. Children are trained to make two sequential button responses in the same order they perceive the sound. So, beep, 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 beep. Using this task, a highly replicable pattern of performance has been found with children with SLI compared to age and IQ-matched children with typical language development. Results show that children with SLI have no difficulty at all with any aspects when single tones are presented. This slide shows the percent correct performance when two tones are presented sequentially, separated by various duration gaps of silence, interstimulus intervals. Results show that there is no difference between children with impaired versus typical language development in their ability to discriminate, sequence, or retain two tones when they're presented with relatively long silent gaps, such as this one with about a 500 millisecond interstimulus interval. However, when the same two tones are presented just a little bit more quickly, with shorter gaps, such as this one with 60 milliseconds, or this one even faster with only 10 milliseconds, the children with the language impairments absolutely fall apart and are basically a chance performance. What's interesting is that this is the time window in which we have to process the acoustics of phonemes and syllables. So let's look again at the acoustic waveforms of the syllable ba and da. Note that these syllables can only be differentiated based on the critical first 40 milliseconds, highlighted here in yellow, where there's a very rapid frequency sweep from lower to higher for ba, or higher to lower in frequency for da. Because of how quickly these formant transitions occur in speech, and the critical role they play in ongoing speech perception, processing the ongoing speech waveform in real time is one of the fastest things the human brain has to do. My studies done using rapidly presented nonverbal tone sequences led me to hypothesize that children with SLI would have grave difficulty discriminating between speech sounds such as ba and da that have formant transitions that require processing in this tens of millisecond time range. When tested, the majority of children with SLI were indeed found to be selectively impaired in their ability to discriminate between these and many other speech contrasts that require rapid auditory processing in this time window, but not those that did not. This result suggested that rather than having a language-specific impairment, SLI children's language deficits may stem from a more primary, non-linguistic, rapid auditory processing problem. To further demonstrate that this speech processing difficulty was specifically related to the rate of change of the acoustic waveform within speech, rather than being phonemic per se, we used computer synthesis for the first time to extend in time the duration of these formant transitions within the syllables ba and da from 40 milliseconds here to 80 milliseconds here, while maintaining their phonemic quality. Remarkably, while less than 20% of children with SLI were able to discriminate between syllables with typical duration, 40 millisecond duration transitions, all 100% could discriminate these with the extended duration transitions. However, it could be argued, and indeed it was, that as speech processing is the fastest thing a child has to do on a regular basis, lack of practice in language itself could have affected SLI children's rapid auditory processing abilities, rather than vice versa. In order to test this, Dr. April Benesic and I began a series of longitudinal studies to assess the auditory processing ability of infants well before they develop language. Our goal was to see if individual differences in the speed of auditory processing assessed in infancy would predict individual differences in language development and disorders many years later. We used the same two-tone sequences separated by the same brief interstimulus intervals that I used in my studies with school-age children with SLI. But of course, infants can't press buttons, so we trained them to listen to a stream of two-tone sequences and then turn their head when they detected the sequence is different. Correct head turns are rewarded. So this is what they do. Once trained, it's possible to very reliably determine for each infant that infant's threshold for the shortest duration silent gap they require between two tones to continue to perform reliably. We call this a rapid auditory processing threshold. In addition to rapid auditory processing thresholds, speech and language skills are assessed every 6 months. Because it's known that SLI can run in families, two groups of infants, one with a positive family history of language impairment and the other without family history, were included in these longitudinal studies. However, many children with developmental language impairments have no family history. This slide shows along the bottom the rapid auditory processing threshold for each infant in this study assessed at 6 months of age, going from the fastest to the slowest. And this is then plotted against the child's language comprehension abilities at the age of 3 years, going from the child that developed the best language to the poorest. Results show a very striking relationship, very high correlation between rapid auditory processing thresholds at 6 months and language comprehension percentiles at 3 years. The faster the auditory processing threshold at 6 months, the better language developed by the age of 3. This is language comprehension. Following these children from infancy through 7 years of age, we found that individual differences in rapid auditory processing predict early language development, which in turn predicted reading development. SLI, unfortunately, has been very difficult to remediate with typical speech therapy. At this point in our research, it looked like we had uncovered a potential root cause for these children's language problems. If this were indeed the case, then we hypothesized if we could provide these children with an intervention that would speed up their rapid auditory processing skills and or slow down the rate of change within the acoustic waveform of ongoing speech, this should lead to significant improvement in their speech perception, language, and subsequent reading skills. In collaboration with Dr. Michael Merznick at University of California in San Francisco in his lab, we developed 2 novel intervention approaches disguised as computer games. Both used individually adaptive, neuroplasticity-based computerized training. The intervention is called Fast Forward. Our first approach was to adapt the Tallal repetition test into a training method for the two-tone stimuli could be presented. For the two-tone stimuli, we developed two computerized sweep tones designed to mimic the acoustic changes within formant transitions. In this computer game, children were trained to press the triangle for one sweep tone and the square for the other. Each child began with two relatively long duration sweep tones presented sequentially with silent intervals that were also long enough for them to respond correctly 80% of the time. And that sounded like this. And they just had to go this one and then that one. They were trained. Successful trials were rewarded and followed by sequences with slightly shorter duration sweeps and silent gaps while errors were corrected. The goal was through intensive experience and practice to train children to process tone sequences at faster and faster rates until they could reach the rates that are important for processing speech. Recall that earlier also I had demonstrated that speech perception of individual syllables could be dramatically improved by extending the duration of the formant transitions within the syllables ba and da. In our second approach in this novel intervention, we capitalized on this discovery by developing a novel computer algorithm in which the acoustics of full sentences could be modified such that the rate of change across the speech signal was prolonged and the fast transition elements were differentially amplitude enhanced. And it sounded like this.
Touch the green circle.
I'll play that one more time.
Touch the green circle.
This algorithm could then be applied to a very wide variety of linguistic training tests similar to those used clinically by speech-language pathologists. As children progressed in the training, the acoustic modification is reduced as linguistic performance improves until the goal is age-appropriate levels of language processing can be reached with normal, fast speech. And that would sound like this.
Touch the green circle.
In a control study, two groups of SLI children, initially matched in age and degree of language impairment, were provided the daily training for 4 weeks, either with or without the computer-enhanced speech and rapid auditory processing training. Results showed first that individual differences in rapid auditory processing thresholds could indeed be significantly improved with training, the red bars here. This was the first study with children to show that a basic psychophysical threshold could be significantly modified with neuroplasticity-based behavioral training. Results also showed that SLI children who received the training with the computer-enhanced speech and rapid auditory processing training, again the red bars, made significantly greater gains compared to matched SLI children who received exactly the same linguistic training but with natural speech, the blue bars. This was shown for standardized clinical tests of speech discrimination, language processing, and even grammatical comprehension, just by changing these acoustics. Subsequent studies done using Fast for Word at Stanford and Harvard replicated these behavioral results with dyslexic children, who also extended them by adding fMRI scans. fMRI scans done before Fast Forward training showed that while doing a rhyming letter task, typical readers, shown here, show frontal and temporal parietal brain activation in the left hemisphere, while dyslexic children showed weak frontal and absolutely no temporal parietal activation. This is a pattern that's seen repeatedly in studies with dyslexics. After only 8 weeks of Fast Forward training, the dyslexic's brain activity was significantly increased so that it more closely resembled that of typical readers, both in the frontal and the temporal parietal area, regions known to be very important for both language and reading. Since its development, Fast Forward training programs have been reliably implemented in thousands of real-world schools and clinics. To date, Fast Forward programs have been used by more than 3 million children in 55 countries around the world. Thank you very much.